Hello, welcome to another video. When we say an integral converges, it means it's possible to calculate the area between the curve and the x-axis, whether it's under or it's above it. We just want to find the area between the curve and the x-axis. But when you say that an integral diverges, it means the area is too large. It's infinitely large. Now, to you, when you sketch the graph, you might think the area is not that large, but it's huge. Let's take a very common example. You see the graph of f of x equals 1 over x. When we sketch this graph, it runs this way. You see, because we don't want to get too close to the x-axis, we leave it this way, and this looks like a small gap. And really, it's a small gap because of the amount of space that we have. But this never touches this, so infinitely, it just keeps going without ever touching the x-axis. And the same thing repeats here. Something like this. Okay? So assuming I want you to find the area under this curve starting from 0 to here. To you, it looks like there's just a tiny space from here to here. But you see this area? Just this area is infinitely large. And therefore, it's not possible. You can't integrate 1 over x from 0 to, let's even say, to 2. Okay? You can't do this. Why can't you do it? Because the area, this tiny area is infinitely large, and that's the meaning of divergence. Okay? That's what it means for something to diverge. So if it is this simple, why is it tough to understand? The problem is, look at these three problems. As I go to infinity, I know that the top of this expression is 1 plus sine something. And I know sine, the maximum I can get of a sine function, the output is either 1 and the minimum is -1, or any number in between -1 and 1. So this number here on top cannot be more than 2 and cannot be less than 0. Okay? But it has been combined with a function. So it is as if we have combined 1 plus sine x, which has a finite value of which is always between 0 is less than. So this is, we can put it this way. This is 0 and this is 2. So this is the finite value you get for the top. But when you multiply it by 1 over x to the e, this guy can go to infinity. So you have a finite value combined with something that gets infinitely large in the bottom, but 1 over infinity goes to 0. So it looks like this should be convergent and this should be convergent, right? We don't know. So that's the problem. We go to the second one. This should be convergent, and 1 over x should also be convergent, right? Now, when we say convergent, remember we're trying to calculate the area. What do you think is going to happen if we try to calculate the area under this line as it goes to infinity? If we restrict it, yes, it looks even like a trapezoid or something. But as you go to infinity, it becomes excessively large. You cannot calculate the area. And so this does not converge even as you go to infinity. It also does not converge if you start from 0. So it's a problem. And that's why you have to know these before you get into trying to solve this. So the most important tool you'll need for this topic is to recognize that when you have an expression with x in the denominator and you have 1 over x to the p, where p is the power, the dominant or the highest exponent of x, or the variable in the denominator, if it is p, if that p is equal to 1 or less than 1, the function you have will be divergent. And if you have your p greater than 1, the function will be convergent. So you can start thinking in your head about this problem, that this is supposed to be divergent. This integral should be infinitely large, and so we cannot compute it. If you go here, you should start thinking, what is the value of e? E is a number that's greater than 1 because it's 2 point. That's Euler's number, 2.718. Then you know that this should be giving us the behavior of a convergent series, whereas this one will be not convergent. Now, when you go here, it becomes a little messy, and that's why I made it the third one. You don't know what's going to happen. This is a parabola. This is definitely divergent. If this is all you have, you don't have the bottom part. As you go to infinity, remember the arms go away from the x-axis, so that's a divergent function. If you go here and you now multiply it by 1 over this looks like it's going to be convergent. So this is a mixture of divergence and convergence in the same expression. So what is the overall ruler? Is it divergence or convergence? So this is the point of this video. So now that I've explained this, remember that this is important. It's the key to whatever we do. The key to whatever we do in this exercise. So let's start with the first question. The first thing you want to think about is, what do I do with this? I've already assumed from the previous explanation that because this is greater than 1, I expect this expression to be convergent, but I cannot prove it. The only way I can show that this expression is this integral is going to be convergent as I approach infinity is if I can show this. That look, if I plot the graph of a convergent function, let's say a function goes like this. It is not increasing, okay? All I need to show is that because the area from here to here is finite, if I can find any function under this one, so let's say I have another function like this, so that this is g of x and this one is f of x. If I can clearly show that g of x for whatever value of x I am dealing with is always less than f of x, then I know that because this one converges, this red one will also converge. Okay? They will converge. They will come toward the x-axis. That's how you have to see it. So don't be confused. You need the function you're solving to be under the function you know. Okay? It has to be less than it. For convergence, it has to be less than the function you know. What function do we know? This is the function we know. This has to be on top. And then whatever you have has to be compressed to converge. Okay? I'm just helping you remember. Okay, so that's the point. Now, what do we know? Based on what I've said, I said that we know that the integral, I'm not going to put the boundaries, just know that I'm going to infinity, then let's just write it. Integral from 1 to infinity of 1 over x to the e dx converges. We know it converges. How do we know it converges? Because of this property that I wrote, that when p is greater than 1, it will converge. Okay? Now, we want it to be as close as possible to what we have here, but how do we do it? Let's do what you call mini squeeze theorem. Remember, recall that sine x is always less than or equal to 1, okay? The absolute value rather, or you can write it this way. -1 is less than or equal to sine x, so which implies, because I want to generate 1 plus sine x, I'm going to add 1 to this, so it means I'm adding 1 to everything. If I add 1 to this, it becomes 0. It's less than or equal to 1 plus sine x, and it's less than or equal to 2. So, because I need the less than part, this function has to be less than whatever I'm dealing with, I am going to take this way, and I'm going to divide both of them by x to the e. So what I'm going to say is that the function on top here is 2 over x to the e, and the function under is my 1 plus sine x over x to the e. If this is true, then this function, this integral converges. If it is not true, I have to go find another way to show that it converges or diverges. But you cannot use convergence to prove divergence, okay? You can only use convergence to prove convergence, okay? If this fails, then we have to think of something else. So now, let's go back to what we're supposed to do. So we need to show that this statement is true. That's all we need to do. So here we're going to say that we're going to leave out the integral. So we're going to say that the integral from 1 to infinity of 1 plus sine x over x to the e is less than or equal to 2 over x to the e with a question mark because we're not sure if this is true. If we keep going, and it works out, then that's fine. Okay? So, oh, by the way, remember, I should have said this. If f of x is greater than g of x, then the integral of f of x is greater than the integral of g of x. Those are just some basic theorems in analysis, but you just have to know that, okay? If 1 is greater than 2, then the integral of 1 is greater than the integral of 2. That's obvious. Okay, now, so here, I'm going to leave out these and just deal with this, okay? It means that 1 plus sine x over x to the e minus 2 over x to the e. I brought this, no, let's just say is less than or equal to, okay? Now, I generally don't like cross multiplying, so what I would do is bring this over to this side and say 1 plus sine x over x to the e minus 2 over x to the e is less than or equal to 0. Less than or equal to 0 means this side is negative. Let's see if it's negative. Since we have the same top, we can now multiply every term by x to the e. So we have 1 plus sine x minus 2 is less than or equal to 0. And what is 1 minus 2? It's going to be negative 1. So sine x minus 1 is less than or equal to 0. This is a statement that's always true. And remember, how do we know it's always true? Because all the values of x we are using are from 1 to infinity. So they're all positive values of x. And we know that sine x, you can even move this over here and say sine x is less than or equal to 1, which is actually part of what we started with here. So this statement is true, and because this statement is true, this is true, and this is true, and this is true, and this is true. And if this is true, because this converges, this has to converge because it is under. That's how you go through the process. Okay? So now we can say, therefore, let's write it here. So we can say the integral 1 over this, 1 plus sine x over x to the e dx converges by the comparison test. And that's it. Because you've compared it to something you know converges. Because this converges. Okay? Now, maybe when I take the next one and the next one, you're going to see how it works. Let's take the next one. So here again, we're going to say we know that 1 over x is divergent. Okay? We know that the integral from 1 to infinity of 1 over x dx is divergent. And what does divergent mean? It means it is moving away from the x-axis. So for that to be useful, whatever you are comparing to this has to be above it so you can move it away. You see that point? Whatever you're comparing it with must be above this one. So you must be looking for a greater than relationship to this one. So, because this is what we have. We have a graph. This graph is going away from the x-axis. So whatever graph you're dealing with has to be above it for it to be divergent. So let's call this f of x. This is f of x, and it is divergent, okay? Divergent. So whatever you're creating has to be g of x, and it has to be above it, okay? So we're trying to establish a greater than relationship compared to this. That's the only way this is useful. If you get a less than relationship, it is useless. Less than is good for convergence, greater than is good for divergence. Come on, that's easy. Okay. Convergence. What's the letter C? Convergence. C. Less than. Don't mix them up. Okay, so now that's what we have. Now, let's look at the behavior of the top. What do you think is happening to this as x approaches infinity? This is becoming smaller. You notice that this expression here, 1 plus e to the negative x, is the same thing as 1 plus 1 over e to the x. As x gets bigger and bigger, this gets smaller and smaller. And the smallest value this can have is 1. Remember, we're going from 1 to infinity. So the biggest that this can be is, actually we shouldn't be looking for the biggest value of this expression. We should be looking for the smallest, because we're looking for a greater than. So anytime you're trying to do a greater than or less than relationship, the one that is greater, try to make it as small as possible, so that you can say, yeah, I even made it smaller, yet it is still bigger. So what makes this smaller? This becomes smaller if x gets bigger. So as this goes to infinity, this is going to go to 0. So the smallest value that this can be is 1. The smallest value this expression can be will be 1. The biggest value it can be will be 1 plus 1 over e, okay, which we really don't need. So the smallest value this can be is 1. So we can actually now start comparing the value. So we can say, which implies that 1 is less than or equal to 1 plus e to the negative x, and this is less than or equal to, what would it be? What's the biggest value can be? 1. That's it. But we want to take the smaller version now, okay? Because this has to be greater than something. So now we're going to divide both sides by x. So here we can say the integral from 1 to infinity of 1 minus e to the negative x divided by x dx is greater than, or I switch this, greater than, so I'm not using this side. It's greater than or equal to 1 over x, the integral from 1 to infinity dx. Okay, with a question mark. If we can prove that these two are if this is greater than this, then it is divergent. Remember, this guy has got to be above. So if this is true, then we're good, because this guy is our guy here, the white guy. Okay, so here we go. We're going to say 1 minus e to the negative x over x. I'm going to move this over here. Minus 1 over x is greater than or equal to 0. Now we can multiply every term. X cannot be 0. We already know, because we're moving x from 1 to infinity. So there's no 0 in this interval. So we're safe. So if you multiply everything by x, we're going to get 1 minus e to the negative x. Why do we have minus? It's plus. It's plus. Sorry. Okay. Is greater than or equal to 0. So this is 1 minus 1. And then we have e to the negative x is greater than or equal to 0. Is this true? Yes, it is true, because any exponential function is always above the x-axis. It's always greater than 0. So this statement is the same thing as writing 1 over e to the x is greater than or equal to 0. This is a true statement because this is always positive, or at least always non-negative, okay? Always non-negative. The only time this even becomes 0 is as you approach infinity, which is part of what we're, so it's okay. So now because of this, we have established that this is divergent. We know that. We have also established that we can connect these two and we have this, so we can conclude and say, therefore, the integral from 1 to infinity of 1 plus e to the negative x over x dx is divergent by the comparison test. Okay, this one is a little tricky, but it's not complicated. So what I'm going to do is look at the top and look at the bottom and look at the dominant powers of x both in the top and in the bottom. So this is how you want to look at this, okay? You want to compare what's on top. The dominant power here is x squared. The dominant power here is x to the fifth, but there's a square root over it. So what you want to look at this is, since there's a square root over the dominant power, it means you have to find the square root of x to the fifth, which is going to be x to the 2.5, right? Just do it that way because that's all you need. You just want to establish whether p is greater than 1 or p is less than or equal to 1. That's all you need to do. So we can say that we can say x squared over, here we're going to have square root of x to the fifth, okay? Which is the same thing as x squared over x to the 2.5. Okay, I just took the half of that. If I simplify this, this would be the same thing as 1 over x to the 0.5. Now let's quickly go here and see, is it here or is it here? Obviously, this is less than 1. It has to be a divergent expression. That's all you need to show, that it is divergent. So go back and say that, what do I need to show? I just need to show that this function is greater than this. Once you can show that this is greater than this for all values of x from 1 to infinity, then this has to be divergent, because that's the only thing we can do with this divergence. So we're going to say we know that the integral from 1 to infinity of 1 over x to the 1/2, let's write 1/2 instead of 0.4 just to look nice, dx is divergent. Okay, how do we know it's divergent? Because of this rule, because 0.5 or 1/2 is less than or equal to 1. Now, once we have that, then we can say the integral from 1 to infinity of 2x squared over the square root of x to the fifth plus 3x dx. We can say it is greater than or equal to, because that's what we need. For divergent, it has to be greater than. For convergent, it has to be less than. Okay, is greater than 1 over x to the 0.5, or let's say 1/2 integral from 1 to infinity. So now, because of the square root sign, I may not want to put the two together on the same side, because I'll still have to move it over and then square both sides to get rid of the square root. So I'm going to write it this way. I'm going to say 2x squared over the square root of x squared plus 3x will be greater than or equal to 1 over x to the 1/2. Now, the signs do change, especially when you have negative numbers. But there are no negative numbers. X is not negative. Remember, we're working from 1 to infinity. So I should not be worried about whether the signs will change, okay? I try to avoid that. That's why I collect like terms on the same side. But now I can cross multiply. If I cross multiply, what would I get? I'm going to go this way. No, let's go this way and divide the board. So let's do this way. So this is going to be, if I multiply this by this, is going to be 2x to the, this is going to be 2.5. Because I'm going to add them together, so I'll leave it that way, is greater than or equal to the square root of, this is x to the fifth, of x to the fifth plus 3x. So now I can square both sides. If I square both sides, what do I get? I'm going to get 4x to the fifth is greater than or equal to x to the fifth plus 3x. Okay, if we bring everything to this side, we're going to have 4x to the fifth minus x to the fifth minus 3x is greater than or equal to 0. This tells me I have 3x to the fifth minus 3x is greater than or equal to 0. And if I factor out 3x, let's write it here. So we have 3x multiplied by x to the fourth minus 1 is greater than or equal to 0. Now, is this statement true? Definitely 3x is greater than 0 because all the x's we're using are from 1 up. And if you look at this, the only time this expression can be 0 is if x to the fourth minus 1 is 0. Yeah, that's if this is 1. So this is a true statement. And because the statement is true, since this is a true, oh, we didn't put a question mark. Come on. Remember, this was an investigation. Okay, don't get overconfident. You have to keep going. And then at the very end, if what you're saying is always true, this is always true because x to the fourth is always greater than or equal to 0. In fact, you can just conclude there that 3x is always greater than 0. Okay, and x to the fourth minus 1 is always greater than or equal to 0, depending on what x is. And this is true. This is a statement. And this is true. So for everything we've done, this is true. So you say, therefore. So remember, is greater than when it's divergent. Don't mix them up. So therefore, we say the integral from 1 to infinity of 2x squared over the square root of x to the fifth plus 3x dx is divergent by the comparison test. It's been a long one. Thanks for watching till the end. Hope you learned something. I'll see you in the next video. Never stop learning, because those who stop learning have stopped living. Bye-bye.